Hello guys, good morning. Good morning to all of you. Hello guys, good morning. Can you hear me properly? Are we good to go? So this is the third part of mathematical tools of quantum mechanics. Actually, many tools are there. That is why it is taking a couple of lectures, but this will worth it. Okay, in long run, you will get benefited from these mathematical tools of quantum mechanics. If a base is strong, you'll be strong at quantum mechanics. Good morning, Harry. Okay, so in the last two classes, whatever we have discussed, if you have any question or query, you can ask. Otherwise, we can start with the next topic. So the topic which we're going to discuss, I hope everything is all right till now. No confusion in anything. The topic which we'll start with today is function of operators. So we have talked about operators. Now, if there is a function of operator, then what you're going to do? Functions of operators. Just a moment. Good morning, Murli. So what you have to do, let us define the function of operator. So if we denote a cap as an operator, then the function of operator will be denoted by f of a. So let f of a be a function of operator, be a function of operator a cap. So now if I consider that if a is a linear operator, we have already defined what is a linear operator. So if a is a linear operator, we can expand this f of a in the Taylor series. We can expand f of a in Taylor series. Okay, we can expand f of a. It is called Taylor expand, or simply we can expand f of a in a power series. In a power series of a. So we'll write different powers of a and along with their coefficient. So what you can write here, function of a, it is like a1, a2, a square, a3, a cube, a4, a to the power 4. So it is there in the plus. So you can write it in the form of summation. N is equals to, let's say, 0 to infinity. If you start with a0, then that is okay. So an, a to the power n. So you can expand it in this way, where these an are the expansion coefficient. Okay. Now let us take an operator. Let us take a function of operator. Let's say if we have e to the power a times a cap. This a is a scalar and this capital this a cap, capital A cap, it is an operator. A is a scalar. Which can be complex or real. Which can be real or complex. So under this situation, how can we expand this e to the power a? can expand e to the power a as, so e to the power a. What we have to do? What you know, n is equals to 0 to infinity. This is like the expansion of exponential series. You know how to expand it. It is a to the power n by n factorial. This is how we expand exponential, right? X to the power n by n factorial. Here x is a times a. So this will become, if you put n equals to 0, so this is 1, but 1 we cannot write, we have to write identity operator, right? Like in dimension analysis also we have seen this kind of thing, or in matrix. 1 we cannot write, we have to write it in terms of operator or unity matrix in case of matrix, plus x, so a times a, x square, a square by 2 factorial. What will be the next term? A cube by 3 factorial, and it will go on. So this is how you represent functions of operators. Let us now go for commutators involving function of operators. So we have already discussed commutators, right? Now if we have commutators which involve function operators, then how will you tackle? Commutators involving function operators. Okay. Let's say if you have an operator A, and if A commutes with another operator B, commutes with another operator B. Till now we have not introduced in this section this function operator. Let's say simple, A operator commutes with another operator B. Then B commutes with any operator function, that depends on A. Okay. So mathematically if you write this thing, how do you write? The first thing, A commutes with B, so commutation of AB equals to 0, and if this is so, it can directly correspond to B any operator function, let's say F, which depends on A. Just a moment. F which depends on A, their commutation will also commute. Now in particular, what we have, these are very simple things, you just need to keep in mind. Let's say f of A, if it commutes with A and with any function with any other function, let's say g of A, how will you represent this? A commutes with f of A to the power n commutes with f of a, and any function operator which depends on a also commute with another operator function which is also a function of a. Okay, so I hope you got this thing. So this much is enough for this function operators. Let us now talk about what will happen if we take Hermitian adjoint of these function operators. Hermitian adjoint of function operators. So if you calculate the adjoint of f of a, the adjoint of, let's say, f of a, how can we represent that? F of a, so you have to take adjoint, means you have to take this dagger. So this is f star of a dagger. You can write it in this way. This is how you take adjoint of a function operator. F of a dagger is equals to f star of a dagger. Now you see, if a is a Hermitian operator, will f of a be a Hermitian operator? So it is not always true. Even if a is an Hermitian operator, f of a may not be Hermitian operator. So this thing you can write it as a note. Look, these things you need to revise quite frequently, otherwise you may forget. So you note that if a is Hermitian, f of a is not necessarily Hermitian. It will depend upon the functional form. This is quite straightforward, although, because f of a can be anything, right? Depending on the function of, depending on this operator a. So it may be Hermitian, it may not be Hermitian. So when it will be Hermitian, you see, f of a dagger is equals to f star a dagger. Now if f star becomes f, then you can say it is Hermitian. So under what condition f star of a dagger will be f of a dagger or f of a? If, look, this thing is, focus on this thing, f star a dagger. Now if you want to call f of a Hermitian, what we have to do? First of all, this f star should be removed. So this should be equals to f of a, right? So a should be Hermitian, so a dagger will become a, and under what condition this star symbol will go? When this function is real. Okay, so you can write one line based on this. I hope this is understood. So we are writing a line based on this. When this f of a will be Hermitian, f of a will be Hermitian only if f is a real function. F is a real function and a is Hermitian. Both the condition will be reversed. Okay, a dagger will become a F star, if it is real, then F star and F are same. Let's take some example. Let's say if you have e to the power a, some function operator. If you take dagger, what it will give you? E to the power a dagger. E to the power I a dagger. So this will become e to the power minus I a dagger. E to the power I a dagger is equals to e to the power minus I a we do not know, so it will become star when you take the dagger, a dagger. You can write it in this way. Is it clear? Any question till now? A star sign represents complex conjugate. Complex conjugate. Complex conjugate means wherever you see I, that will be replaced with minus I. That is taking star means. Okay. Now let us talk about some relations involving function operators. Let's look, if we have two operators A and B, if they do not commute, it directly means that B and function of operator A will also not commute. Now there is a very important relation, e to the power A B e to the power minus A. This is a special form. So what does this expression produce? Sometimes question come from this, e to the power A B e to the power minus A, this is equals to, so it will give you an expansion in this way. Firstly, B plus commutation of AB plus 1 by 2 factorial commutation of AB. This will keep on increasing in this way, plus 1 by 3 factorial. What will be this? It is like adding the previous term to it, A cap, then you write this one, A cap commutation of AB, this bracket closed, then this bracket closed, and so on. So you can imagine it in this way. you wrote B cap, then commutation of AB, and after this the previous term is you can say incorporated. A, commutation of A and this, next commutation of A and this previous term. So the next term will be commutation of A and this term. Okay, so this is a very important relation involving function operator. If you have given two operators A and B, if they do not commute, then you can write it in this way. If they commute, then there will be no meaning of it. If A, B will become 0, then this series will vanish, right? You see, this will become 0, commutation of A and 0 will be 0. So it will only be equal to B if they commute. So this equation, this expansion holds only when A, B do not commute. Let's talk about inverse of an operator. Inverse of an operator. So let's say we have an operator A, its inverse is denoted by A inverse, and we can say that A inverse exists, and we can confirm this existence of A inverse by this relation. If this relation holds, A inverse A, this is similar to the matrix inverse, A inverse A equals to I. I is the unit operator, you already know it. Unit operator, unity operator. An operator that leaves any state unchanged, that is the unit operator. So this is the inverse operator. Sir, is it B to the power A? Where? On the left hand side of the equation. No, only B. A to the power A cap, B A to the power minus A cap. Let us talk about unitary operators. So these are very similar to what we have learned in mathematical physics. Here just matrices are replaced by operators. That is the basic difference. Otherwise things are very similar. So if you have a linear operator, let's say U, a linear operator U is said to be unitary. It's said to be unitary when if its inverse U inverse is equal to adjoint U dagger. Okay. So U dagger is equals to U inverse. If you multiply U, pre-multiply U on both sides, this will become U dagger, U inverse, and what you know, U inverse will be identity. So unitary operators will satisfy this equation, right? U dagger is equals to U inverse is equals to I cap. Now there are some conclusion from this. What will be the product of two unitary operators? Product of two unitary operators. Product of two unitary operators, what do you think? It will also be unitary. Now let's say we have two unitary operators u and v. U and v, they are unitary operators. So we can write u dagger is equals to I, and v dagger is also equals to I. Now product of two unitary operators will be u v. If you want to show them, what you have to show, what you have to show, u v product of operators, u v dagger. It should be identity as well if the product of the two unitary operators is unitary. So you see, this will be u v. Now you know when you apply dagger, it applies from the right. Okay, so this will become v dagger, then u dagger. U v dagger is equals to how much? v dagger is equals to identity, isn't it? v dagger, let's keep it here, u dagger. So v dagger is identity, so it gives you u dagger. U dagger is also identity, so you can say that the product of two unitary operators is also unitary. Okay, so we can also write it u v dagger is equals to u v inverse is equals to identity. As simple as that. Now this result can also be generalized. It is not about only two operators. If you have more than two operators, then also this result will be valid. So this can be generalized to any number of operators. This can be generalized to the product of or to any number of operators. Why does it take too much time to omit? That means if you have multiple operator product A, B, C, D, and so on, more than that, the product of it. So how do you check? A, B, C, D, let's say dagger. So you see A, B, C, D, and so on will come first, and you see the dagger will come. So then it will become D dagger, C dagger, B dagger, and finally A dagger. Okay, so A dagger will be 1, B dagger will be 1, C dagger will be 1, D dagger will be 1, and in this way 1 means identity, it will give you identity. So you can see, you can expand it or you can generalize it to any number of operators, and still you will get the product of them to be an unitary operator. If it is clear, then we can quickly move forward to eigenvalues and eigenvectors of operators. You already know it, but in terms of operators, how it looks like, that is the main thing. So the topic of discussion is eigenvalues and eigenvectors. Eigenvectors of an operator. This is pretty simple, nothing is there. If you know eigenvalue, eigenvector of a matrix, then it is just in terms of operator. Let's say you have a state vector or ket, state vector or ket. So ket psi is said to be an eigenvector or eigenstate, also called eigenket or eigenstate. Okay, many similar synonyms are there of an operator, let's say A. So a state vector ket psi is said to be an eigenvector of an operator A if the application of A to psi gives, as usual, A operates on psi, it will give you eigenvalue small a psi. This A is a complex number. Complex number is very general, okay. If you take a star and if it gives you the same number back, we can say that that is real. Otherwise, complex is the more generalized one, where A is a complex number called the eigenvalue, of A. Okay, A is the eigenvalue, psi is the eigenvector. This equation is known as the eigenvalue equation or eigenvalue problem of the operator. So if you solve this eigenvalue equation, this is the eigenvalue equation, and if you solve it, what you get? You get eigenvalues and eigenvectors. This equation is known as eigenvalue equation and solution of which gives the eigenvalues and eigenvectors of A. A simple example, if you want to take, that will be the example of the identity operator. If you consider if you apply identity operator on some ket psi, so it will give you back psi. It means it has an eigenvalue of 1. Eigenvalue is 1. Look, if A operates on ket psi, it produces 8 psi, let's say. Then if you apply it n times, means a to the power n, applying on psi, what will it give you? What it will give you? So you see, A square if you apply, so A will again come. Each time A psi will come. So A square A cube, and in this way if you apply it n times, it will become A to the power n ket psi. And let's say if you apply a function operator f of a on this ket psi, this will give you not a but f of a ket psi. Okay, this is f of small a. Look, a particular example of this thing. Let's say a applying on psi is equals to a psi, and it directly means if you apply some function operator, let's say e to the power I a cap, this is a function operator applying on ket psi, so this will give you e to the power I a ket psi. Try to follow what is happening. The eigenvalue of operator a is small a, so e to the power I a will produce e to the power I small a as the eigenvalue. Now regarding this eigenvalue and eigenvector, you can I think you have understood easily this eigenvalue and eigenvector. There are certain theorems which we will just write, and that is sufficient for us. Okay, theorems on eigenvalues and eigenvector. Okay, so this is the theorem, let's say 1. For a Hermitian operator, just note it down. For a Hermitian operator, all of its, these are like the characteristics of eigenvalue and eigenvector put in the form of a form of theorems. So for a Hermitian operator, all of its eigenvalues, you already know about this. Okay, eigenvalues are what? Real. And you know the eigenvectors. What about the eigenvectors? The eigenvectors corresponding to different eigenvalues, are orthogonal. This one we know from the matrix mechanics also. Let's go for theorem 2. The eigenstates of a Hermitian operator define a complete set of mutually orthogonal, means each one will be orthogonal to other. Mutually orthogonal, the eigenstates of a Hermitian operator define a complete set of mutually orthonormal. It is also normal, orthogonal plus normalized, that is orthonormal. Complete set of mutually orthonormal basis states. The operator is diagonal, means only the diagonal elements are non-zero. The operator is diagonal in the eigenbasis with its diagonal elements. Diagonal elements will be the eigenvalues, right? The diagonal elements equal to eigenvalues. While reading this, you will feel that we have already done it in matrix. The basis set is unique if the operator has no degenerate. Degenerate means equal. Okay, let's say 1 1 2. So 1 is a degenerate eigenvalue. 2 2 3. 2 is a degenerate eigenvalue. 5 1 5. So 5 is a degenerate eigenvalue. If the operator has no degenerate eigenvalues and not unique, when it will be not unique? If it has degenerate eigenvalues. Not unique, in fact it is infinite if there is any degeneracy. Then we can express it in infinite ways. Okay, this is the second theorem. The eigenstates of a Hermitian operator define a complete set of mutually orthonormal basis states. The operator is diagonal in the eigenbasis with its diagonal element equal to eigenvalues. The basis set is unique if the operator has no degenerate eigenvalues, means non-degenerate eigenvalues, and not unique, in fact it may be infinite also, if there is any degeneracy. So this is the second theorem. Let's go for the third theorem. Theorem 3. Now this one is quite important. Sometimes questions are set from this. Let's say if we have two Hermitian operators. If two Hermitian operators A and B, these are the two Hermitian operators A and B, if they commute, so commutator of AB will be equals to 0, and if A has no degenerate eigenvalue, means no eigenvalues are equal. If A has no degenerate eigenvalues, under this condition what will happen? Then each eigenstate or eigenvector, each eigenvector or eigenstate of A will also be the eigenstate of B, is also an eigenstate of B. So under which condition? The eigenvector of A is eigenvector of B if they commute, and if A, let's say, doesn't have any degenerate eigenvalues. Under these conditions, this will be satisfied. In addition, we can what is happening? Construct a common set of orthonormal basis, a common orthonormal basis. Orthonormal. Look, orthogonal and orthonormal are two different things. Orthonormal means orthogonal as well as normalized. We can construct a common orthonormal basis that is made of the joint eigenvectors of A and B. Joint eigenvectors of A and B. So this is the third theorem, quite interesting. if two Hermitian operators A and B commute, and if A has no degenerate eigenvalue, then each eigenstate of A will also be an eigenstate of B. And furthermore, we can construct a common orthonormal basis that is made of the joint eigenvectors of A and B. Two more theorems are there, small theorem, you don't need to worry about it. So these are the big theorems. Now these are small. Theorem 4. We told that the eigenvalue of the Hermitian operators are real. What about the anti-Hermitian operators? The eigenvalues of an anti-Hermitian operator are either purely imaginary, not zero. Purely zero is for Hermitian, no? Anti-Hermitian are either purely imaginary. Purely imaginary means what? What is the difference between imaginary and purely imaginary? Purely imaginary means there will be no real part. Let's say 1 plus 2i. So this is imaginary. If you only have 2i, 3i, minus 5i, so these are purely imaginary. Only this imaginary part is there. These are purely imaginary or equal to 0. One last theorem in this context, theorem 5. The eigenvalues of a unitary operator. The eigenvalues of a unitary operator are complex number of moduli equal to 1. So we have also talked about it in matrix part. The eigenvectors of any unitary operator, the eigenvectors of a unitary operator that has no degenerate eigenvalues. This part is a little bit theoretical, but that's it. The eigenvectors of a unitary operator that has no degenerate eigenvalues are mutually orthogonal. So this is very similar, okay, what we have discussed here in case of Hermitian. So that is equally being valid for unitary. So if there is a real part also, it is called imaginary complex number, because you have told that there is a term called purely imaginary, so I don't understand the difference between imaginary and purely imaginary. Yeah, so complex number in general, what is the form of a complex number? It is x plus iy, right? So, you know, this is the real part of a complex number, and this is the imaginary part of a complex number. Okay, so in general 2 plus 3i, so this will be a complex number. Now purely imaginary means this part will be missing. Okay, purely imaginary means only iy part will be there. So whether you have I minus I plus 2i minus 5i, all of these are purely imaginary because x is 0 here. Now understood, Karthik? Now there are a few small topics, but which might have been complicated. So I'm just giving you one ultimate formula from those small topics, but it may be useful in solving numericals. So this is finite unitary transformation. So from this finite unitary transformations, you can just remember one formula, and this is very similar to what we have done here. Look at this: e to the power a b e to the power minus a. So there is a similar formula. Instead of e to the power a, finite unitary transform. Okay, e to the power I alpha g. G is the generator of the transformation. A e to the power minus I alpha g. G is another operator, A is the operator. So you can write it in a similar fashion. So the way we have done it, it will be A plus. Look, this constant I alpha will be multiplied. I alpha commutation of G A plus I alpha square by 2 factorial commutation of G, then this one commutation of G A plus what you're going to do, I alpha cube. Okay, I alpha cube by 3 factorial. Here G will come and this whole thing G A. This bracket closed, this bracket needs to be closed, this bracket is closed, plus so on. So you remember that where G is a Hermitian operator. G is a Hermitian operator that generates this transformation. That generates the transformation. And alpha is a real scalar parameter. So this, I think you will now be able to write it in this way, whatever problem you are given. So one you have done with just a simple e to the power a, sorry, e to the power b cap, sorry, e to the power a cap, e to the power minus a cap. Here you have done it with some constant. This is finite unitary transformations. Okay, now the next thing is quite interesting and important. Now things will be a little bit simpler. Matrix representation of gates, bras and operators. So matrix representation, till now we have not write them in terms of matrix, but now we'll write in the form of matrix. So matrix representations of, your battery is running low. Oh, I forgot to switch on the charging. Matrix representations of gates, bras and operators. Laptop, when it is on charging, it gives better performance. On battery it doesn't work so well. Okay, so you see, let us consider a complete set of linearly independent vectors, means basis. Consider a complete and orthonormal basis. So too many information is encoded in these two words, complete and orthonormal basis, which is made of. Now you are able to understand this term. Whenever I am using this complete, orthonormal, you are getting an idea, right? Previously you were not getting, hopefully. Now you are getting it well. Consider a complete and orthonormal basis which is made of an infinite set of kits. So you see, this is a general thing. In Euclidean space, you see I cap, j cap, k cap. These are the three basis vectors. They are linearly independent. So we are taking it now a general set of complete and orthonormal basis, which is composed of infinites. Instead of 3, there are infinite kits. Let's say phi 1, phi 2, phi 3, and so on, phi n, and so on. So we denote it by this whole thing. We can denote it by a single phi n within second bracket. It will give you the set of this infinite set of kits. Now you see, this set is discrete, phi 1, phi 2, phi 3. So you can count them. So this basis, this is discrete. Now remember one thing, they are orthonormal basis. So what will be the value of phi n, phi m? Can you tell me? Orthonormal means what? Scalar product of phi 1, phi 2 is 0, phi 2, phi 3 is 0, phi 3, phi 4 is 0, phi 4, phi 5 is 0. So if you want to write it in general, what will you write? You will write in terms of the Kronecker delta, delta nm. So it is 1. If you take n is equals to m, it will be 0 if n is not equals to m. Do you understand? So phi 1, phi 2, phi 1, phi 2 will be 0. So that is orthogonal condition. Phi 1, phi 1, that will be 1. Phi 2, phi 2. So scalar product with itself will be 1. And if you take 1, 2, 2, 3, 3, 4, anything, 1, 3, 2, 4, then that will be 0. This is the Kronecker delta symbol. Kronecker delta. Now here a very important term is there. Don't miss this. This is the very crucial term, the completeness condition. The completeness, or also known as closure. The completeness or closure relation for this basis is given by, look, n is equals to 1 to infinity. Okay, phi n, ket phi n, bra phi n. This will be identity. This is known as completeness or closure. This is very important. Completeness or closure. N is equals to 1 to infinity, ket phi n, bra phi n equals to identity operator. Identity operator, you know that if identity operator operates on any ket, it will leave the ket unchanged. Now we'll try to represent kets in matrix representation. Kets in matrix representation. This is very interesting. Just try to follow. You'll understand eventually. No more, not a big deal. Let's say we have a ket psi. So only unchanged kets are with identity or the whole term. Yeah, if this whole term is equals to identity, it means if you apply it on some ket, that will remain unchanged. What does it mean by unit I cap applying on psi? This will leave psi unchanged. So writing this and replacing I with this whole thing, that will also be same thing, na? Let's say this is the ket psi, and we want to represent it in the base of, in this complete basis phi n. Okay, so what you can write? Look, as I applying on psi gives you psi, so we can represent ket psi as I applying on psi. Now I is what? I is this closure relation. So n is equals to 1 to infinity phi n applying on psi. So what is this? What is this phi n psi? Phi n psi is a n, and this ket phi n is remaining. This one, do you understand? I think most of you will not understand, but let me know if anyone has understood this, why we have written this. Anyone? This is a n phi n, where the coefficient a n which is equal to phi n psi. What does it represent? It represents the projection of psi onto phi n. Bra operate with ket psi. Yeah, that is one thing. An is the component of psi along the vector phi n. Look, this is like, you can understand it in this way. A ket psi is equals to a1 phi 1, a2 phi 2, a3 phi 3, and so on. Let's say an phi n. Okay. Now, if you want to calculate this coefficient, what you gonna do? When it is 1, it is 1 when these coefficients n, these numbers n and m, these are same, means phi 1 phi 1 or phi 2 phi 2, phi 3 phi 3. Scalar product is 1 only when these numbers are same. So if you take, let's say, the scalar product of, let's say, phi 1 of psi, so this will be a1 times phi 1 phi 1, a2 times phi 1 phi 2, a3 times phi 1 phi 3, and so on. So you see, out of this term, which term will survive? Which term will survive? Obviously this a1 term will survive, because phi 1 is 1, this 1 2 unequal, so this will become 0, 1 3 unequal, every term will be unequal except this one. So if you want to calculate any of the coefficient, you have to take the dot product. Okay. So let's say phi n psi, what will be phi n psi? What will be phi n psi? Phi n psi. So all the term will vanish. Phi n phi 1 is 0, phi n phi 2 is 0, all the term will vanish, only an phi n phi n, this term will be 1, so that will be an. That is why phi n psi is equals to an. Now is it all clear, crystal clear? This is a very important one. Now if I take this to represent the state psi, okay, so let's say, so is it clear now, Murli, Hari, Karthik? Within the basis, let's say phi n, the ket psi is represented by the set of its components a1, a2, a3, and so on along phi 1, phi 2, phi 3, and so on respectively. Hence psi can be represented by a column vector, represented by a column vector. Ket will be represented by a column vector and bra will be represented by a row vector. will be represented by a column vector which has, because this base is infinite, you will have the column vector which has countably infinite number of components, infinite number of components. Okay, so now you understood how to represent it in matrix. Psi, it is a vector or eigenket. So this is the equation. So this will be written in the form of matrix. So first is A1. So how will you get A1? By taking the scalar product of phi 1 with psi. A2, phi 2 with psi. A3, A4, A5, An, and it will go on like this. So this is equals to A1, A2, An. This is how you represent the kit. Now in a similar manner, if you want to represent a bra, how will you represent? Bra in matrix representation. So kit is a column vector, okay, and bra is a row vector. So bra psi, what does it mean? Bra psi, you can write it in this way. So it is a row vector, okay. So again psi phi 1, you see, because this is a bra psi, so bra psi is coming first, so you have to take the scalar product with phi 1. So this will give you A1 psi, bra psi phi 2, A2 bra psi phi 3, A3, and so on, bra psi phi n, An, and so on. Now there is a twist here. You see, bra psi, so when it will come out from the bra, it will come out as complex, okay. So this psi phi 1, we can also represent it in phi 1 psi star, and phi 1 psi is what? A1, so this will become A1 star. Psi phi 2, so phi 2 psi star, phi 3 psi star. This is a property of a scalar product. Property of the scalar product, we can write it in this way: phi n psi, and so on. So what will be this term? This will be A1 star, this will be A2 star, A3 star, so on, An star, and so on. And this is quite obvious, you know. This what do you do? If you want to convert a kit into bra, you take complex conjugate, okay. So that is why you get this result. What just has happened to ये काम क्यों नहीं कर रहा है दोस्तों? Just a moment. It has started to work again. Now let's say you want to represent a scalar product. We have two kits. Let's say psi phi. This is psi. This is phi. These are two kits. Now if you want to represent, let's say psi phi. For psi we will represent with a1, a2, a3. For phi we will represent with b1, b2, b3. Psi phi, this is bra psi. Bra psi means it will be in this way. You see a1 star, a2 star, a3 star. So this will bra psi will be a1 star, a2 star, a3 star, and so on. And ket phi will be b1, b2, b3, and so on. This will be a column vector, this will be a row vector. So this is equals to, you see, a1 star b1 plus a2 star b2 plus a3 star b3. So we can write it as sum of an star bn, sum over n. So what is bn here? Can you tell me? Bn you can get, look, phi is written as b1 phi 1, b2 phi 2 plus b3 phi 3 plus b4 phi 4 dot 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 plus bn phi n. So bn will be obviously when you take let's say phi n and phi, this will give you bn, isn't it? If you want to write b2, then it will be the scalar product of phi 2 and phi, b3 phi 3 phi. Now we have represented ket, bra, and let's now represent operators. Operators in matrix representation. Is it getting heavy, or should I go a little bit more? Look, for each linear operator, let's say A, we can write, let's say A can be written as I cap, A, I cap, right? Now what is I cap? Using the closure relation, we can write n is equals to 1 to infinity ket phi n bra phi n A, again n is equals to 1 to infinity phi n phi n. So this will become sum over n m. Achha, here we have used n, so let's use m here. So phi m phi m. So this can be written as a nm phi n phi m. Where a nm is the n by nm matrix element of the operator A. Okay. Now A, it is an operator. Let's say it is a n by m matrix, n number of rows, m number of columns, let's say. So the element matrix element. How will you write those matrix element? Those matrix element you can write it with this formula: A nm is equals to phi n A phi m. So if the basis vector is phi n, then you can write it in this way. If it is given in terms of psi, you can write it in other way. Okay. So A nm, so phi n A phi m, where phi of phi n within the second bracket is the basis. So let's say we have this operator A. It is represented in the basis of basis is important. Let's say phi n. This is an infinite set of linearly independent vectors. So we can represent it by a square matrix. By square matrix A. So A is what? A11, A12, A13 and so on. A21, A22, A23, so on. A31, A32, A33 and so on, and here it will be so on, because we have infinite number of elements in the basis. So it will be like this. So a common element you can if you want to write, let's say A22, what will be write? You will write phi 2 A phi 2. If you want to write, let's say A31, what will you write? Phi 3 A phi 1. You know how A will behave acting on phi 1. Whatever you will get a ket here, and that ket will be taken with this phi 3. If you want to write, let's say A13, it will be phi 1 A phi 3. So let's summarize this. If you want to represent operators, let's say we have an operator A is represented as matrix A whose matrix elements Aij is defined as. How will you define? Let's say instead of phi, if you are given un as the basis, so you can write ui a uj, or let's keep it as phi only, phi I a phi j. This will be the element Aij in phi I basis. Now if you want to write the transpose of this operator matrix, the transpose of operator A, so it will be represented by A transpose. Now what will be the matrix element of this A transpose? Aij transpose. So obviously it will become phi j A phi I. Okay, just reverse. It was phi I A phi j for Aij. Aij transpose phi j A phi I. Now if you want to calculate the Hermitian or adjoint, then also this will be applicable to it. Okay, too much theory we have done. Let's go for a problem. Problem is simple. Okay, theory part seems to be a little bit odd and complex, but once you understand, you will find the problem to be super easy. Let's say if S is okay, if the operator S is defined as S operating on U1 is equals to U3, let's say. S operating on U2 is equals to U2. S operating on U3 is equals to U1. Furthermore, Ui Uj is equals to delta Ij, means they are orthonormal basis. Ui Uj delta Ij, I j may be 1 2 3 and so on. So the first thing you have to do, construct the matrix S. You have to construct this matrix S, and furthermore, once you are done with it, you have to prove that S is Hermitian matrix. Okay, can you do this? Give it a try. So the basis is Ui. So what will be the matrix elements? Matrix element, if I write Sij, it will be simply Ui S Uj, isn't it? And the matrix S is represented by S11, S12, S13. Sorry, A 1, 2, 3A. So your dimension is defined. Only 3 terms will be there. S21, 22, 23, 31, 32, 33. So what you have to do? You have to find out S11, S12, S13. Can you do it? What is the matrix? This is the matrix element. S11, U1, S, U1. So S applying on U1 produces U3. So it is U1, U3. U1, U3 is not equal, so it is 0. S12, U1, SU2. SU2 is U2. So U1, U2, 0. S13, U1, SU3. This is 1. S21, S applying on U1 is U3. So U3, 0. Is it difficult? What answer are you getting? A supplying one U2 produces, you can write it from here, it is already given U2. A supplying one U3 produces U1, so it is 0. 1 no 3 1 3 2 3 3. Okay, last term. Is there any confusion, guys? So what is the ultimate matrix? S is equals to, where did you get 1? S1 3 you have got 1, here you have got 1 1, here you have got another 1, here you have got another 1, and all the elements are 0. It means S1 3, 1 3 is here, 2 2 is here, and this is 3 1 is here. So this is anti-diagonal. Okay, all other terms are 0. It is not diagonal. Diagonal, this diagonal means it is talking about principal diagonal. It is like this, you can say other diagonal, not the principal diagonal. So the first part is done. Now next part, if you want to prove whether S is a Hermitian matrix, so you can take S dagger. What will be the value of S dagger? So this row will be in the column will be in the row. So 0 0 1. So 0 0 1, 0 1 0, 1 0 0, 1 0 0, and you can see it is basically the same. Enough. S dagger is S, so we can say that S is a Hermitian matrix. Anti-diagonal. I don't think is there any term like anti-diagonal? Does it exist? Just let me just check it. What does this called? Yes, it is called anti-diagonal or secondary diagonal. Okay, this is a primary diagonal, principal diagonal. This is a secondary diagonal, or also known as anti-diagonal. Yes, anti-diagonal is a thing. Okay, guys. So I think this is sufficient for today. One more class I think we require to complete this. In the next class, we'll be mainly solving problems. Okay, mathematical part is over. Okay. In the next class, we'll be solving problems from commutators and all. You will find it interesting. Okay. With this, let's end the session here. Thank you, guys. Thank you very much for joining the session. Bye bye. Take care. And always like the video, even if you don't like. The like button should be pressed. Chalo, bye.